So hi, and in this video, let us just continue off from where we left in the previous video. So in the previous video, we basically discussed till the basic response of the standard first order low pass filter, and now that I have just drawn or written the response of a standard high pass filter also for comparison. As we can understand, the only difference here is that this high pass filter has a uh, zero at DC, right? So it has a zero at DC, so it's quite simple to understand that basically, as we know, this property that if we have s multiplied to some Laplace function, then in time domain it basically just translates to its time derivative, right? So we know this. So we can, since we already know the impulse response, step response, and the ramp response for low pass filter, so similarly we can just easily obtain these response for high pass filter by simply doing the differentiation. So these are the responses, and here we can say that there is nothing to be surprised about really. We can do it mathematically also. For example, if I wanted to find a step response, right? If I wanted to find the step response, I would have simply multiplied 1 by s and then found the inverse. So if you observe it, it is just also equivalent to the impulse response of a low pass filter. So we can see that these two match. Right, so there is no surprise in that. Similarly, if I wanted to find the ramp response from high pass filter, so again these S and S would have had cancelled, and it would have looked as if I'm trying to find the step response of a low pass filter. So we can see again that these two quantities match. So there is nothing surprising about this, right? So again, if we try to see it graphically also, so we can understand that for a unit step function, what will basically happen is that the high pass filter will try to track the instant change, but it won't be able to track the steady state or the DC component. So eventually, it will decay out like this, right? So it is quite simple to understand. Also, one more thing that I should be mentioning is that as we said that for a low pass filter at the zero time, it will behave as a pure integrator. So similarly, this high pass filter also at t equals to zero will behave like a differentiator. And I don't think so it's again anything to be surprised about. Again, we can take a simple example that we have this ramp input. So in response to that, what we are getting is a growing slowly growing a unit step function. And if we observe it closely, then we know that the derivative of this guy is a straight line only, right? And we can actually establish that at near t equals to zero, the behavior will be like that. So now that we have mentioned all of this, there are some more important intuitions that I think we should quickly discuss. One thing that we must realize always is that, um, for example, if you have a capacitor and if we have an inductor, there are two things that we must realize. What are these? Is that we already know the basic relation that a capacitor's voltage V of C is given by Q by C. So we know that if there is a change in this voltage, then that much current will flow through the cap, right? Like what I'm trying to convey is that the rate of change of the voltage across the capacitor will be given by the current by C. So what we need to realize here, the important takeaway here is that if there is a sudden change between the plates of the voltage of a capacitor, then an impulse current will flow through the cap, right? That is the important thing we need to understand here. Similarly, for an inductor, we know that the relation is given by what? It is given by the voltage across the inductor is given by V of n is given by n and derivative of the current. So again, here also we must understand that the voltage, the voltage the rate of change of current basically determines the voltage, right? So alternatively, I can actually write it as, right? So again, here also what you must understand is that there is sudden change of voltage forced upon the capacitor, then an impulse current will flow through it. And similarly, if a sudden change of current is forced to the inductor, then impulse voltage will appear across the inductor. Again, we usually say that a capacitor would allow an impulse, a sudden change of voltage across it, but you in a steady state. But there can be scenarios when sudden change of voltage across the capacitor plates can happen, which actually happened in this example, right? So if you look at this example, and we can see that in this response, there is a impulse also over here. So if I sketch it again properly, so what we are actually seeing here is that at zero time, we are having an impulse in the positive direction, and then this will this is decaying out. Now if you think about it, if we try to find this step response intuitively, as we typically say, what you would do, you would try to find the initial value by using the initial value theorem, and the final value by using the final value theorem, right? So if I just apply the final value theorem here, I have already the transfer function over here. So if I just simply try to apply the final value theorem here. So basically that is this multi, and then I'll say that s will tend to 0. So we can understand that the final value is 0. And again, similarly, if I try to find the initial value, so I have to substitute it with infinite, and what I'll then get is half, right? So here we can see that this initial value final value theorem is not predicting the initial value theorem specifically is not predicting the impulse. And why is it so? It is the exact limitation of the initial value theorem, which basically is that if the function or the response has an impulse at the t equals to 0 time, or at the initial time, then the initial value theorem won't be able to predict that impulse. Similarly, the final value theorem will fail when the system is unstable, but that means that it won't have a steady state value at t equals to infinite. So that is something you must realize. So we got this value and we got this value, but still we could not get hold of what is this impulse. Now, the question is that can we intuitively understand when this kind of impulse will be seen? So we already discussed this condition that when there is sudden change of voltage across the plate of the capacitor, some impulse current will flow, right? So because we know that a sudden change, if you are finding the derivative of voltage and it is changed suddenly, then this term will become an impulse, right? So that is something that we understand. So here also the same thing will happen. So here in this particular question, an initial condition is given, right? And I actually ignored it. I should have considered it. So it is 1 volt, right? An initial condition of 1 volt has been given. So again, mind you, this initial value theorem or this transfer function is usually sketched for what? This transfer function is sketched for no initial conditions, right? So the initial value theorem that we applied again, that also won't account for the initial condition. So again, here I must add the initial condition and the final value will be 3 by 2. So this value is 3 by 2. But again, still it won't be able to predict the impulse. So let us understand what is happening physically in the circuit. Initially, this plate of the capacitor is at 0 and this plate of the capacitor is at 1. So basically the capacitor effectively has a voltage of -1 across it if this is positive plate and this is negative plate. The moment when this input goes high, then this plate becomes 2, and that means that the capacitor voltage changed from -1 to 1, right? So has been a sudden change of voltage. Since there has been a sudden change of voltage and the magnitude of that sudden change is 2, that means an impulse of what? An impulse of 2 divided by C will flow through this cap, right? And since this capacitor is at 1 volt, so there is no need, so this capacitor will try to maintain that 1 volt across it at the instance of t equals to 0 when this input went from 0 to 2, which means that this entire impulse current will flow through the resistor. And since it is entirely flowing through the resistor, because of that, we will see this impulse, right? The magnitude of this impulse will be 2 by C times R. So that is the main idea, that this magnitude of impulse will flow, will appear at the output, and then eventually what will happen that since now this cap has 1 volt across it, and this cap has 1 volt across it, and then we can by an initial condition also be predicted that eventually this cap this cap will have 3 by 2 voltage across it. Alternate way to visualize this is that this sudden voltage change will force del V and del V change across the two, and thus 1 volt and 1 volt additional will appear across these caps, as we discussed in the previous video. But how this impulse is coming was important to figure out. But then again, this begs the question that if we want to intuitively comment whether some impulses are happening or they are not happening in the circuit, how do we always get an intuitive feel of them? Because obviously, when we are trying to just look at a circuit and predict its behavior, we can definitely, it's easy to miss this impulse at the start, right? So, number one is that this impulse behavior, we'll see this impulse behavior at input, we'll typically see only for a high pass filter, right? We usually see this for a high pass filter. But as we are seeing here also. But again, is this argument fully correct? The main idea is this only, that if there is a sudden change of voltage happening across the plates of a capacitor, then some impulse current will be flowing. But here, since this impulse current flowing entirely to the resistor, which determines the output, that's why we are seeing an impulse. But okay, let us try to change the scenario a bit. Let us, like, for example, let's simply have these two caps, right? If we simply have these two caps and we are trying to observe the output over here, then we can understand that these capacitors will instantly just stay at 3 by 2 and 1 volt respectively, right? Because there is no discharge path for them. Okay, now that is something that we understand. But what will happen if there was no initial condition? If there was no initial condition also, then also would have had, would we have observed an impulse? Now that is a good question. Why? Because now understand, if I have this particular kind of a setup, and there's no initial condition in the cap. So now here what will happen is that when I'll apply a step of 0 to 2, then uh, at certain infinite frequency, what is happening is that we are forcing 1 volt across this and 1 volt across this, right? This is something that we are forcing. And again, one may argue that this cap's voltage is suddenly changing, and so it will carry an impulse current. Correct. But now what we must understand is that even this cap's voltage is going from 0 to 1, and so it will entirely, this impulse current will flow through here, and this guy, no current will flow through this guy, and at the output, what we'll directly observe is 1 volt. And then eventually this voltage will decay out and there will be no impulse in this particular scenario. That is something that we must understand. So here, the important takeaway is that here, the main culprit behind this impulse was also the initial condition, which prevented this capacitor voltage from changing suddenly. And because of that, from changing all of a sudden, and because of that, we saw this impulse. But again, safest, the safest route uh, would be to solve it mathematically and then come to the conclusion that this is happening. But this was just a kind of a way to gain an intuition as of why the circuit behaved the way it did. All right. So now let us go to the next topic, which is the realizable first order transfer functions using passive components. So we can understand if it's passive component, that means that it won't have any gain, right? Which implies that the transfer function, whatever transfer function that we are building from passive circuit, it won't provide any gain, which implies that HFS will always be less than 1 or at most be equal to 1, right? So this is a typical general first order transfer function, and now we'll just try to compare that what values of zero and pole are possible in this circuit, right? So we can understand that this zero can have three values. That is, it can be at DC, it can be at infinity, or it can have any intermediate value. Similarly, pole can also have three values, which implies that we can have nine possible permutation combinations for this first order transfer function. Now, what we'll say is that if we have zero, if we have the zero present at zero location and you have pole also present at zero location, so how will it look like? It will look like just S by S, right? Because this is at zero, here it is also at zero. So clearly, this transfer function is a constant, right? This transfer function is a constant, and thus basically it does not have any dynamics of first order system, and thus we have to remove it. Similarly, if our zero and pole are at infinity, right? Then again, that is a constant transfer function, so it won't qualify, right? So again, I should basically mention it again that for a passive component built transfer function, it will be less than one, right? Because if it is equal to one, that means that this zero zero and infinite infinite conditions will also satisfy. But clearly, the we want that the system is not a constant system, right? We want it to have first order dynamics. This again, from this also we can also explore a very interesting problem. For example, if I have this kind of a circuit where the R and the RR and the L values are the same, and we are trying to find the transfer function over here. So you can understand that since this impedance is same and this impedance is same, then the transfer function is just half. So again, even this circuit would exhibit any first order dynamics, right? It will be just a constant function. Again, this is something that you must understand. And despite the fact that here the zero and the full locations were not at a zero or infinite, right? Did I say it? Did I say it correct or did I say it wrong? So here, as we understand, it basically the zero and full location will cancel each other out, right? So despite these kind of criteria not being met, still it will behave this way. So now, let us discuss some more possibilities. So next is that we have some intermediate value of zero, and we have pole at infinity, and as, uh, we have zero at zero location and pole at infinity. Again, these won't be possible because if pole is at infinity, then that means that system is zero order. Again, understand in this particular transfer function, if I substitute omega p as infinite, then this term vanishes, right? And then it no longer is a zero order system. In fact, it will be a system which looks like 1 by s plus omega z. And now this function for frequencies greater than DC will have a gain which is more than one. So again, it won't satisfy the criteria of a passive circuit, right? Cool. Again, even if your h of zero, let us say h of zero can be one also, right? So we can understand that in a general scenario, it won't be able to satisfy the passive criteria. And again, in reality, no system can exist, RC or RL system can exist, which is only a zero, because zero was because of some inductor or a capacitor, which would inherently have a pole two along with it. So a zero order system is not a possibility over here, right? Unless it was a constant system like the example that I gave earlier. Then these are other possibilities that if pole is at zero. Now, what is the problem of pole being at zero? Is that if pole is at zero, then at zero frequency, the gain will be infinite, right? Because see, this is the basic structure, right? If pole is at zero. If this guy is zero, then at DC, the gain of the system is infinite, right? Again, something that is not acceptable. So this basically eliminates six combinations, and we have three combinations left. What are those three combinations? So combination number one is that zero is at infinity and pole is some finite value. Zero is at zero location and pole is some finite value, and both the zero and pole are finite. Cool. So all these scenarios are fine, but now let us try to discuss about this guy. Let us try to discuss about this guy. And why I'm saying so is that let us try to discuss that what will happen for this transfer function when s tends to infinity. So when s tends to infinity, the transfer function will look like h of 0 omega p by omega z. That is the value of this transfer function at infinite frequency. So let us say that h of 0 is 1, let us assume. So this means that at infinite frequency, this transfer function will be less than 1 only when the 0 frequency is more than the pole frequency, right? So that is one condition that I have established over here. And if pole frequency is greater than 0 frequency, then this also kind of determines that whether this transfer function will be valid or not. But typically, what we expect is that the magnitude of the zero is more than that of pole to like short ensure that the system is possible, right? But still, we can have possibilities where the zero is less than the pole. Zero is less than the pole, and it can still be a passive circuit, but then again, the initial value of the transfer function or the value of at the DC of the transfer function will be such so that this condition is impressed. Correct? So, still, in the end, to conclude that these three transfer functions will still be possible, and I think it's fairly enough to identify also, like, right? So, I don't think so that there is anything strange or weird about this discussion, but we just try to give it a mathematical picture. Now here again, this is a simple function that has been plotted over here, and what we can see here is that this is the simple low pass function, and this is the Bode plot as expected and at the pole. The slope is minus 20 dB per decade, and if we see the corresponding phase plots, we understand and we know that at pole frequency, the phase is basically pi by 4, which eventually decays down to minus pi by 2. And at pole frequency, it was minus pi by 4. Why? It's because at pole, S is equals to omega p, right? So we know that tan inverse omega by omega p, we can easily find it out. It's not a big deal. So tan inverse of 1 is 45. That's why the minus 45 angle at the pole frequency. Same argument will be for 0 also, and at 0 it will be plus 45, and eventually it will try to reach 90 degrees. So this is the scenario in which the pole frequency is more than the zero frequency, and this is the graph we are seeing, and we are specifically mentioning that it is 0 dB. So this transfer function, passive transfer function, is possible only when at most this graph is less than 0 dB, right? And again, this is the phase that we have discussed, that it will be initially pi by 2, at pole it will degrade down to pi by 4 and eventually 0, right? So this is something that we have discussed. And again, since this phase is always negative, it's the lagging transfer function. And since this function always has a positive phase, it's a leading transfer function, right? These are two things that we understood. Again, one more thing we should understand is that the slope of a integrator, right? And this is the slope of a differentiator. Correct. So these are again two things that we must understand, that this is the slope of differentiator. So uh, typically we can also comment what we can comment what we can comment is that this system, this high pass system, it can be also be said as a leading system, and this low pass system can also be said as a lagging system. But again, why we are saying it is because of the phase response, right? So here we can actually mention this that uh, lagging system and then the leading system. Right? Okay. So now let's move further. Let's move further. And here we had discussed some more transfer functions. So here, basically, where omega p is less than omega z, and we are seeing that this guy is lagging, right? And here, this is leading again because of this only. That here we have this minus 20 dB, or basically a negative slope, which corresponds to an integrator or a low pass, and here we have positive slope, which basically corresponds to a high pass, right? And it's intuitive also here. Why? See, it is not strictly a low pass because again it has some finite dB magnitude. But what I'm trying to say here is that the low frequency response is stronger than the high frequency. And here the high frequency response is stronger than the low frequency. And that's why the slope, from the slope, we can loosely comment on whether the system behavior is integrator like or differentiator like. And again, here also we are seeing the same thing. And one relation that again is good to remember, which we derived above also, is it's good to keep in mind that h infinite is but divided by h of 0 is equal to omega v by omega naught. Why? We don't really need to memorize it, but it's good to have it at the back of our head. Why? Now, just by looking at the pole and zero, we can actually comment on the response of the system, right? Like, for example, if the pole is larger than the zero, then we can know that the response will be something like this because the final value is larger. Similarly, if the zero is more than the pole, then we know that the initial value will be larger than the final value. So this is the kind of intuition that we'll be able to build. And again, we are talking about the magnitude over here, right? Uh, so it's not even necessary that we're talking about magnitude. Let us say that one of these guys is opposite in sign. That is, if we have a RHP 0, then again, for example, if I have a RHP 0, then again, if we know that our final value will be positive and we had a RHP 0, which is basically this guy will be negative, so you can understand that our response will be something like this, right? So these things are not really that hard once we understand that how this formula came about. So just by looking at the point zero location, we can basically predict on the response of the system. And this is something that I have drawn here also. Right? Cool. Now one more thing that we must understand is that we can basically break any general function into high pass and low pass component, and that will basically simplify our life more. Cool. Now we have example of this circuit, and we are to find its response. Already I have sketched the answer, but let us try to come at this result by intuition. Okay, so now when I force a sudden change at the input, what will happen is that this capacitor, this is sudden change will feel as if it's shorted. This capacitor will feel as if it is shorted, and this capacitor will feel as if it is shorted. And thus, this impulse current can easily flow through this path, and no current will be needing to flow through the resistance. And that's why at initial time we won't find any impulse, right? That's the main reason because all this impulse current can easily flow through this capacitor series network. Because of this, now one third of this voltage will appear, and since the sign convention is plus minus and the initial voltage appeared like plus minus in the opposite direction, so we'd have minus 1 by 3 Vx. Cool. Next, at infinite time, this guy will be open, this guy will be open, and this guy will be open. So the steady state current will be able to flow in this direction only. So definitely, we'll have 1 by 3 Vx at the Is this a first order system? Yes, because if I remove this input, we can basically lump these energy storage elements. Alternatively, we can also understand that the energy stored by this cap is dependent on these two caps, and similarly, energy stored by this cap is dependent on these two, and energy stored by this cap is dependent on these two caps. So basically, all of these are energies are not independent with respect to each other. They are not independent energy storage elements. That's also this is a first order system, and that's why this kind of a dynamics is what we would expect. One more important thing that we can understand from the circuit is that see that the initial condition, see the input to the circuit was like this. So we know that if we would have a LHP0, the LHP0 would have only helped my response. That is, my response should have grown from somewhere here. But since we can see that the response is starting from minus the value, it is opposite in the direction to the input. That means that the circuit has a RHP0. So this is also something that we could predict simply by looking at the output response of this circuit, right? So this is something cool that we observe. Great. So this being said, we can do this as an activity later on that just for inspection, try to find the transfer function of the circuit, provided now that we know that how it will behave. But even if we did not consider this behavior to begin with, because still we should be able to comment upon the transfer function of the circuit, which we will do shortly if time permits. Okay. Now, we will just talk about the pulse response of the simple low pass and high pass filters. Again, I hope that it is quite simple for people to realize that this is a low pass filter and this is a high pass filter. So these kind of things now should be at our fingertips because these are not that hard to tell, right? Cool. And here I have just written some things. For example, a punch chain can be defined by this expression. A pulse chain can be defined by this expression where this function p of t is basically this guy. Okay, so if I have one square wave, then uh, I can define this function like this, right? If this is a p of t. So um, the Fourier transform of this will be sync clearly. And then I have just tried to find the Fourier transform this entire pulse train, which happened to be this guy, right? Where D is the duty cycle. So here I have just mentioned that when the duty cycle of the pulse is half, then the Fourier transform of this will have only DC and odd components, right? And if the duty cycle is not exactly half, then we can have both odd and even components. Basically, if it's a rectangular pulse train. Then, alternatively, what we must understand is that for a square pulse train, we'll have only DC for unipolar wave and odd harmonics. What is meant by unipolar wave? See, if it is 0, 1, or only 0, minus 1, or only 2, 3. Basically, the sign of the wave is same. That's a unipolar wave. So for a unipolar case, the harmonics of the pulse train will have DC harmonics also, and otherwise it will have only odd harmonics. But more thing we must understand is that this is strictly true only for half the duty cycle. And for other duty cycles, we can have odd and even components both. How did this come about? This came about from this expression that we came up with that the Fourier transform of the pulse train will be this guy. So it's just a sync function. I think we all know what a sync function looks like, right? So we can easily sketch. Sorry for the bad diagram, but we can understand that how the sync function looks like. So and we know it's zero crossings too, like because we all know, right, that we can express this sync function as sine of whatever argument is inside this divided by this argument, right? So this is basically how you can sketch a sync function. And from this also, this idea basically came about. Okay, so now that we have briefly discussed about the Fourier transform of the pulse train, let us discuss about the low pass and the high pass responses. So here we have mentioned uh, tau. So what is tau? Tau is basically the time constant of the circuit, right? Which is basically RC for a RC circuit, and it's L by R for an LR circuit. So what we understand is that the time constant is small, that means that the charging and discharging in the circuit is fast. And if it is large, that it means that the charging and discharging in the circuit is slow. That only what I have done is that if I have a impulse train which is sketched in blue as the input, so it will, for a low pass filter, it won't be able to track the sudden high pass change, which is 0 to Vx, but eventually it will be able to reach the steady state or the Vx value and before the time t, right? Because this is t, right? And then it will also be able to easily decay out also. And I think that's what is happening. But in other case, when the time constant is less, then by the time the charging has happened to some intermediate value, the charging has happened to some intermediate value, the input already swung down to the lower value. So now it will try to discharge from here slowly, and again it won't be able to fully discharge because the charging is slow, right? And this will keep on happening, which is kind of a ripple about some mean value. Here I just written we expect to, for example, right? For high pass filter, same thing will happen is that it will be able to track sudden high frequency change, but it won't be able to track the steady state change. And since the response of the circuit is fast, so this is the kind of response we can expect. And here, for the when the charging discharging is slow, so again it will be able to track the high frequency change, but it won't be able to discharge fully, right? And thus, this circuit will look as if it's a square pulse only, but of half the amplitude in this particular example, because it will be able to track the high frequency change, but it won't be able to reach the full Vx value, and thus it will then start to decay, but that also not fully, because again the response of the circuit is slow. So that is the overall qualitative idea of what will happen when the LPF or HPF is subjected to uh, uh, pulse stream. And again, let us keep in mind that here we are just discussing about a simple low pass filter, or if I rather draw it by this transfer function, the transfer function is this, and here it is also simple high pass filter where the transfer function was this, right? Again, we can solve this mathematically also, and the way to go about it mathematically is that just try to solve it for one interval. That is, just try to solve it for one interval. And what you can visualize this problem as is a unit step like this, and another unit step which is shifted by t by 2 if this entire interval is t, and then this, and then you can just apply superposition, right? That you just try to find the response for this, and then the response for this negative unit step. Does this work? Let us quickly talk about this. We know that for a high pass filter, the response to a unit step, what is the response to a unit step? We have already discussed it before, that the response to a unit step is a decaying exponential, right? We have already discussed this. So you can understand that we'll have a decaying exponential. And here also, we can understand that since a negative state will be a negative decaying exponential. That is what we have sketched, right? And then when this step will come about, when this step will come about, so we should be able to understand that again, same thing will go on and on. So we should be able to understand that this pulse trade is a combination of it's a combination of these uh, of these various step functions only. in positive and negative side. And same thing argument can be extended for the low pass filter also. But again, as I have mentioned before, uh, here since some dynamics in the input are involved, so you must keep in mind whether the time constant or whether the speed of the circuit is high enough compared to the time period of the input. Cool. So now that we have discussed this, we can discuss about the impulse and ramp response of some of certain first order circuits, and we can discuss that now briefly. Again, here I've just mentioned that we can visualize a high pass filter as just a all pass filter, which is basically constant minus the low pass filter. So these are quite standard things. Now, let us try to discuss some examples, and then we can maybe briefly discuss the other circuits. Okay, so now this is the first example that we have, and we are feeding a impulse impulse input to it. But before going into the details, here I just briefly mentioned something that a voltage impulse can be defined just by a flux. And why is that so? Is because if you integrate a voltage, what you obtain is flux. And we know that integration of an impulse is equals to the magnitude of the impulse, right? That's why I have defined this voltage this way. Similarly, integration of the current is charge. That's why I have defined the magnitude of an impulse current as Q. Quite simple, right? Now, here, just by the look of it, typically they will mention also, but this is basically a voltage impulse. Now, let us try to discuss the behavior of the circuit. So, at infinite frequency, what will happen is that this capacitor and this capacitor will short, and basically voltage division will happen. Also, since this capacitor is larger, this implies that lesser voltage drop will happen across it, right? And since at steady state, these resistances will do the voltage division, so half the voltage will try to appear across this network, right? So typically for a general input, what we can expect is that this circuit will have a lower initial value and a greater final value. Can we infer something about this circuit by looking at this juncture? Is that the is that the pole of the circuit is lesser than its zero? But that is fine. But when I talked about this h of infinite by h of zero, and I'm saying this omega p of omega z. What I said is that at infinite frequency, it will be 1 by 3, right? And at DC, it will be half. So at DC, it's half and it's 1 by 3. You can understand that the pole of the circuit is less than the zero of the circuit. So that is what I wanted to quickly tell. But again, you can understand that since impulse is fed here, so it will be a decaying exponential in some sort, right? So that's what we have actually we showed here also. Good enough. But now I think I have done multiple examples of it. I've drawn that at t equals to zero time. T equals to zero time. Okay, so basically, I just tried to build some intuition when I was doing this. But okay, uh, we can understand that some okay that some 5 by 3 5 by 3 will be over here and okay. Okay, cool. So now let us try to deal with this particular question. Okay. So now what will happen is that when we feed the impulse to the circuit, what will basically happen is that a sudden at that sudden point of time, only a portion of that impulse will appear over here, which is 1 by 3 times that impulse, right? As I said, and this will happen at t equals to 0 time, right? And now, because this sudden impulse has appeared across this capacitor, what will happen is that this sudden impulse will force current across the remaining network, right? Because we know that 5 by 3 impulses over here, so we know that 2 5 by 3 impulses over here. As a result, what we will say is that certain currents will flow now in this circuit, right? Because now, since this impulse has vanished at t equals to 0 plus, so this guy will short, right? And this guy will short, so the circuit will look like this only, right? Correct. The circuit will look like this only. And now, what will happen is that the currents will start to flow in the circuit. So if this current is I, since this is R, and this current, so this current will be 2I, right? And how did I say that this current is I and this is 2I? How did I directly say that this current is I and this current is 2I? I said it very, very simply because the voltage across this resistance at that instance is 5 by 3, which is I, which is 5 by 3. And that's why I'm saying because of this I current will flow. And voltage across this resistor because of this capacitor is in opposite direction. It's twice. So that's why I'm saying that 2I current will flow. And now at t equals to 0 instance of time, we can just quickly apply our KCL, and from that we'll obtain the initial voltage, which is 5 by 9 RC. Cool. And then it will eventually decay out. Again, here again we can understand a failure of the initial value theorem, that as per the initial value theorem, we would have simply said that 5 by 3 current would appear, but again that will not be a simple constant value, it will be an impulse. That initial value theorem does not exactly tell us. So here again we have to use our brain, right? So here again we have to use our brain, that since impulse has been fed and that impulse is being divided capacitively through voltage division, so the output also will have an impulse again in this case. So this is something that we must realize, right? And when that impulse has vanished, what will be the dynamics in the circuit is also something that we must realize. So after that sudden impulse, it won't decay from here, but because of that impulse, now that impulse voltage will induce some that a sudden impulse which is now gone will induce some currents in the resistors, and because of that, the t equals to 0 plus voltage of the value of the voltage will be something else, and then from there it will exponentially decay. So that's why this example is kind of important to understand. Again, let us go through this example again. What we are saying is that if we feed an impulse voltage to this particular network, what is going to happen is that this impulse will, with this impulse itself will be undergo voltage division, which is 1 by 3 of that impulse, and this capacitor will have twice of this value, and then this impulse is gone, right? So this means that this guy is shorted to this, and this will be the equivalent circuit at t equals to 0 instance. And now since this value is 5 by 3 voltage across this capacitor at t equals to 0 time, that means it will induce some current I across this resistor. Similarly, this value of voltage is 2 5 by 3 and is in opposite direction. Thus, it will induce 2I current. And if we just simply apply some KCL over here, by that standard KCL, we will be able to come to the conclusion that the initial value of the output voltage at 0 plus time is this, right? So that is the basic idea. That is the basic idea over here. Great. Again, can we sketch the transfer function of the circuit quickly? Yes, we can actually do that. So we know how to find the pole, so we can just short this guy and CC will merge together. So it is just 3C, and the resistance will go in parallel. So it will basically be 3RC by 2. And this is the time constant which will yield the pole of the circuit. And does this circuit have a zero? So again, one very quick way to one way the way that we discussed that whether the circuit will have a zero or not is that only that imagine this is Z2, this is Z1, so Z2 plus Z2 plus Z1 is the transfer function. So the only thing now that we need to check for is that will Z2 go to zero when Z1 has not gone to zero? Yes, it will go to zero at this frequency, right? So this is the basically the transfer function in the circuit, but this is not the entire transfer function because at DC, what will happen at DC, these terms will vanish, but we know that at DC, the circuit's response is supposed to be 1 by 3, right? So 1 by 3 term, I'll just multiply it outside. Now, is this is this correct? How can we check? Is that at infinite frequency, the circuit must uh, basically be giving half, right? So at infinite frequency, the circuit must be giving half, and that is also at infinite frequency, circuit must be giving half, and thus we can understand that it's 5 by 9 here. Okay, I think I did some silly mistake while plotting the transfer function of the circuit. We'll do it shortly, don't worry about that. But before we'll sketch this transformation quick enough. I did some silly mistake. We'll just get back to it very quickly. Again, mind you, I'm just doing a revision myself also, so that I'm prone to doing some silly mistakes now and then because I just woken up also. So I'm in a bit of a sleep at this point of time, but it's fine. Okay, so for a ramp response, we can see that the low pass filter will respond like this and high pass filter respond like this. There is nothing crazy or sacrosanct about this. And then I have just given another example where we have uh, this particular circuit where the transfer function is given by this. Could we sketch it very quickly? Yes, the pole would have been given by this, and zero would happen when this particular guy will go to infinite, right? And which will happen at RC, 1 by RC, and this is the transfer function. And again, at DC, the value that the circuit should give is half, and at infinite frequency, the circuit must give the value of 1. So this transfer function satisfies that. And here, what we are basically seeing is that here the pole is greater than 0, which implies that h of infinity will be greater than h of 0. Okay, and it is quite kind of expected also in the ramp response. And here, what we are seeing is that in this particular circuit, the ramp response grows like this, right? And here we have just written the ramp response for this general circuit, which is V naught m times h of 0, and this is the general ramp response that we have sketched. But I think that we could actually derive it quite simply also. So memorizing this is not that important. Yeah. Then I had just written something about a lagging system that like this is clearly a lagging system, right? And you can basically model this just by a low pass filter and out subtracting the output of a low pass filter with a high pass filter. And this is what we have done in this circuit. As we can visualize, is that this portion is a low pass filter, and this portion is a high pass filter. And if we just subtract the two outputs together, we will have a lagging system. And this is the ramp response of that. And we can clearly see that the circuit is lagging, right? The circuit is lagging. Here, the circuit is leading the input, right? So that is something that uh, we discussed in the end. Now, let us talk about the transfer function of the circuit now. Okay. So again, let us try to sketch the pole of the circuit. So the pole of the circuit will be or the rather the time constant associated with this will be R by 2 and 3C. Yes. And the zero of the circuit will be when this guy, either this guy goes to zero, or when this guy goes to infinite, right? So what I basically want to convey over here is that this transfer function is simply 1 by 1 by r 1 plus s 2rc, right? So this is the transfer function, and we can understand is that this transfer function will go to infinity. It will can go to infinity, but this transfer function won't go to zero. So that means that zero is not present at zero frequency, right? We are quite something obvious. So, but the only condition that we need to check is whether this transfer function will go to infinity, which it will at RC time constant, right? And this is what we sketched. Now, at DC, the behavior of particular behavior of the circuit. So at DC, what's going to happen is that only half the magnitude will be able to pass, right? And at infinite frequency, one third of the magnitude will be able to pass. And now, yes, we have sketched the correct transfer function, right? So whenever you're trying to find transfer function by inspection, you can always do these kind of sanity checks. So that was the transfer function of that particular circuit. And again, we could solve it mathematically also, but again, solving like this by intuition is always faster. But again, predicting these impulses, or dealing with impulses and all is kind of can be tricky at times. So we have to like always really delve into the physics as of why things are happening the way they are. Okay, now let us briefly I just discussed about some RL circuits. So we know the standard relation that flux through an inductor is given by its inductance times the current, and this flux can be written like this, which is written like this by Faraday's law, right? Quite simple. And here I have written that current can't spike unless you are manually forcing it through the inductor, maybe by means of a current source, right? Now we know that this is the time constant of the inductor, and here, like akin to capacitor, we apply flux sharing and flux conservation as we did for charge conservation. Again, this is the Faraday's law, and Faraday's law talks about EMF, and Lenz's law talks about the current. This ninth sign actually comes from the Lenz law. Right, and Lenz's law basically said that when you subject an inductor to a change of flux, then the direction of the current is such that it opposes that change in flux. And it is basically energy conservation only, because if the current is induced uh, such that it will support the change in flux, then that flux will keep on growing, right? It is just creating energy from nowhere. So that's why this Lenz's law basically just tells about the sign or the direction of the current that is induced because of change in the flux of the circuit. Now, this M is the mutual inductance, the Scape's coupling coefficient, and L1, L2 are the values of two inductances. And this basically comes in handy when you have two inductors in series, let us say. This dot basically represents the sense of winding. Like you can wind a circuit like this, or you can wind a circuit like this, right? And we can represent them by uh, by dots. So if the two dots are on the same side, that means they are both wound in the same sense. And at that time, I have to indicate it with the same color actually. And at that time, the series inductance becomes L1 plus L2 plus 2 twice of the mutual inductance. Why? Because this flux interacts with these flux of the inductors interact with each other, and that's why the overall inductance of the circuit seems to be this way. Typically, in many simpler cases, we don't consider this M, but this is the overall general expression. Here, when I've drawn dots in red, the inductors are wound in opposite sense with respect to each other, and at that time, the series relation becomes L1 minus L2 plus 2A. Same thing I've done for inductor combination in parallel also. And here we can see that this numerator will remain the same regardless of the sense of binding, but this minus sign will come into play when they're bound in same sense, and plus sign will come when they're bound in opposite sense. Cool. Now here I have then just sketched the transfer function of this particular circuit, which we simply did by finding its pole in zero and silently check whether this transfer function is correct or not. We can just check this transfer function at DC, which should be half, okay? And at infinity, it will be 2 by 3. And yes, it is 2 by 3 because 4 by 3 into half will be 2 by 3. So that was all about inductor, and every other argument will apply as we applied in RC circuits. One more thing that we should know, which is quite also simple to realize, is that this is a high pass filter and this is a low where you're observing the output over here and input over here. Why so? Is because at DC this inductor shorts and at infinity this inductor opens, which means all the voltage will appear here, and that's why this was a high pass filter and this is a low pass filter because at DC this current will short and all voltage will appear here, and infinity this inductor will remain open. Why? Why is that so? Is something that we can intuitively understand from the current expression that the inductor follows, right? Some other things also that we understand is that inductors impedance is omega times L for steady state or for sinusoidal or for phases. So all these kind of things we must know. And the general expression for the impedance of an inductor is S times. So these kind of things we know already. So I won't be like keeping putting too much of time in that. Now what I want to see is that have I left anything that I said? Yeah. So here I said that we should discuss the transfer function. Can we, like for example, if there is a problem in front of us that we are not to find the output response of the circuit, but we have to just sketch its transfer function, then how would we go about it? So the circuit looks like this, right? So the resistance is here, some cap is over here, some resistance is over here, then some resistance is over here, some cap is over here, and here we have some input. So when finding the pole, since it's the first order system, we can first of all just short this, right? Now the moment I short this guy and this guy together, what will happen is that I can now sketch the circuit in a more simpler way, right? Because it can be hard to visualize what is going on. So we'll just sketch this circuit in a more simpler fashion. And what is going to happen now is that this is the capacitor, this is the resistor, and uh, this is shorted, right? So basically, since okay, I'll just change the color of pen. Since what I want to convey is that since this guy is shorted, so this resistor and this cap and this resistor will come in parallel, right? So this cap and this resistor came in parallel. Now what will happen that this node is connected to this parallel combination of R and C again. Is connected to this parallel combination of RC again, right? And this C and R is then in parallel with this entire guy, right? This C and this R is parallel with this entire guy. So what you can do in this scenario is see. So here we can understand that finding pole is not that straightforward, right? It's not that straightforward to find the pole in the circuit. It will demand some calculation, right? You won't be really able to like determine it just by inspection. So we can find it by actually trying to numerically solve this circuit. We can actually try doing this by actually trying to numerically solve this circuit. But at for time being, just so that this video does not go too long, I'll avoid this for time being. Okay. Uh, Next is let us just quickly go through the summary that I have made. So Yeah, so this is a standard transfer function. This is the relation between its value at infinite frequency and zero frequency. Then initial value theorem basically fails if there is an impulse at the initial condition itself. It, why I'm saying it will fail because it won't be able to predict that impulse is existing. And finite value theorem requires the system to be stable, right? So these are quite some standard things. Now, if there is some sudden jump in output at in a circuit which does not have any initial condition, then we can from that intuitively figure out that the circuit has a zero. Okay, and uh, this sudden jump can happen for this sudden jump can it happen for an impulse is the question. So that for impulse input, this sudden jump can happen. But we are talking about inputs other than the impulse, right? We are talking about inputs other than the impulse. Now, uh, now that we have discussed this point, here I just sketched some basic. I've just written about some basic differential equations for series RL and series RC. These are very quite easy to obtain. So not a big deal about these. Then here I have just written that impulse current can cause a sudden jump in inductor current, and impulse voltage can cause sudden jump in capacitor voltage. I have written this. So again, it's not something something out of the world that I've written. Again, for a decaying exponential, which is of this form, we already should have some idea of this that at tau time or at a time constant time, this function will be at its 37%, right? For twice for two at for time, uh, basically what is this? This is the value of time, okay? So when the time is equals to two time constants, then this function will be at 30% of its value, and it will decay subsequently to 1% of its value. So typically we say that at 5 tau, we say that the transient have died out. Again, when we are trying to sketch the response, what we say is that let us say that you have decaying exponential and it starts to decay at a time t equals to t naught time. Then at t naught plus tau time, or let us say if it was decaying at zero, it started to decay at zero time. Then at tau time, what we can observe is that if you draw a tangent to that value at the initial time, this tangent will cross at the time constant. Same thing actually happens for a similar thing actually happens for a growing exponential, which is basically of the unit step form, is that at the initial condition I draw a tangent, it will cut, it will cut the straight line, which is which it will cut the line which is horizontal line, which basically corresponds to the steady state value of this particular function. And if you then extend this line to the time axis, it will again be the time constant only. I think I'm clear in what I tried to express is that for a decaying exponential, if you draw a tangent at its initial condition, that tangent will intersect time axis at after tau seconds or after tau time. And similarly, if you have a unit step function which is basically growing towards some steady state value, then again a tangent at steady state will intersect the horizontal line corresponding to its final state at a time corresponding to the time constant, right? So this is what I wanted to convey. Then we know that fundamentally all these RC, RLC, all these circuits are fundamentally differential equations, right? And because these differential equations are sometimes harder to deal with, that's why we migrated to the Laplace domain to begin with. But we know that when we try to deal with this differential equations themselves, they the response of those differential equation can be expressed by a complementary integral and a particular integral. The complementary integral is also the homogeneous solution where basically, for example, if I have this differential equation, so this term will be zero, right? And this, so basically what we understand is that with the zero input response, or the natural response, right? Natural response is basically the complementary integral. It's also the transit response, and the particular solution or the particular integral, the steady state response or the forced response, which we calculate by considering the presence of the input. And we have already studied various techniques of how to find particular integrals or complementary integrals in our childhood. Like one of the ways is that if we wanted to find the solution, a complementary integral of this particular differential equation, we could have just replaced the differential operator with operator d, and we could have just written it as what? We could have just written it as t plus tau, and I would have come outside because di is basically I dot, and then we would have just equated this to 0, and then d would have been equal to minus tau, and then the solution of this guy would have been what? E minus t by tau, right? So this is how you can actually solve this, right? So we know how to solve these standard complementary integrals and particular integrals. So this is one another way of looking at it. Now, let us also just discuss this quite quickly that what is the first order response to a sinusoidal input? So here we must understand that since we are applying a sinusoidal input, so at steady state, the steady state of the circuit is basically a sinusoid only, right? And since we are suddenly applying a sinusoid, so initially this sinusoid won't exactly appear at this circuit's output. Here we are just trying to see the current itself. So it's kind of a simpler case, but we can understand that if we were to find the voltage, let's say across this inductor, which basically inherently makes it a high pass filter, so it would just would have in this current I times the impedance of this inductor. So it's not again a big deal. Good enough. So again, here also I have just solved it by this method only that I just said that we can express it, the current flowing through this inductor as a complementary integral and a particular integral, and this complementary integral will be given by this guy, and this particular integral will be correspond to the steady state solution, which will be a sinusoid. Okay, so that will just have its phase shifted by some degree, and it will have its magnitude manipulated, right? So this particular integral can be easily found by boundary conditions, right? So like we know that at initial time there will won't be any suddenly the sinusoid so it won't be appear in the circuit, right? Because this inductor will oppose that sudden change of current in the circuit, and because of that we can find the values of this a and b constant, and at infinite time the circuit will be in steady state. And so we can say, we can just by phasor analysis, we can say that what will be the value of this D, right? So it's just simple phasor state analysis. There's nothing great about it. And then thus we can just then write the final solution of the response of this RC circuit to a sinusoidal input, which was just this decaying transient and a steady state course, right? So it will just be a sinusoid will just grow gradually and eventually reach its steady state. So we could have had alternatively solved this circuit by just using Laplace also, but the limitation of Laplace would have had been that we would have not been able to capture this transient component in the Laplace analysis, right? In the transformation analysis rather. Now, as I was mentioning before, okay, so now I have written more about capacitors. So here, when I close, when I close this resistor, so I'll say that the voltage across this capacitor will decay exponentially. So is writing it as exponential times ut is correct. So it's obviously wrong because ut basically means that this capacitor voltage is decaying like this. But you must understand that when this capacitor becomes pre-charged, its voltage is actually some at some finite value, even at negative time, and then it will decay, right? So that's why this ut must be used very carefully, right? That is the idea that I wanted to convey. Okay. What else do we have in store? So here I have some other circuit. So what I have done here is that at t goes to 0 time, I have opened the switch. Okay. And we are trying to understand that what will happen in this circuit. Okay. But we can, so this is the scenario that maybe I'll dedicate some separate video for this maybe. Okay. Because it is just another interesting dilemma that I just wanted to discuss. I maybe I'll do it later. And finally, I've just written some notes about Laplace transform only that we know that S can be written as this decay factor term and the frequency of oscillation or frequency of the input. And this is the decay term, which is in Nepo per second, right? And again, since it's a decay term, so this guy has to be zero for the overall Laplace setup to be convergent in nature, right? And uh, so again, this is the same thing which you already know that for a linear time invariant system, if I fed this kind of a input to a circuit, then the only the amplitude and phase will change, but the S will fundamentally remain unchanged. And that was the idea that I wanted to convey. And here I have just done some simple phasor analysis for the same. Good enough. So I think we have revised all of the first order circuit, and in next video we'll discuss about second order circuits. So I think we have revised quite a lot in this video, and if anyone was watching, thanks for watching, and maybe I'll see you in the next video. Thanks.